I'm Emma Tejević. I'm Access and Partnerships Manager for Data Science Conference, and I'll be there as a tech support during the tutorial. I want to introduce you to our tutors, Andrej Miscic and Luka Vranjes. Andrej is a chief scientist and Luka is a data scientist and at Valira AI. And they will hold the LLM applications with LangChain tutorial. So enjoy. You can start.
Okay, great. Thank you, Emilia, for the introduction. Let me just share my... Wait, host disabled. I cannot share my screen. It says that host disabled participant screen sharing.
Wait a minute. Okay, I think now you can do it. I've made you a host.
Yeah, great.
Okay.
Is good? Okay, great. Thank you. Okay, so welcome everyone. The name tags here on Zoom are a little bit messed up because we're both on the same computer. Even though it says Luka, my name is Andrej. I'm joined here with my colleague Luka. And today we will try to introduce you to LangChain through some practical examples to see how you can develop applications around large language models. Okay, so who are we? Like I said, I'm Andrej. I'm joined here with my colleague Luka. We are data scientists from Valira AI. Valira AI is a Slovenian data science provider that offers custom solutions in the fields of artificial intelligence, machine learning, and more general data science. We are active across different subfields of machine learning, from computer vision to forecasting. But me and Luka, we primarily work on applications of natural language processing, which is also the topic of today's workshop. So like I said, the goal today is to have a beginner-friendly, more introductory tutorial in which we want to introduce you to a framework called LangChain and do that through actual practical large language models applications that you might encounter in practice in your work. In order to do that, we prepared this agenda. First, we'll start with some short theory, not really theory, but we'll just introduce what LangChain is and similar frameworks for that matter. Why are they necessary? And what do they offer to developers? Then we'll go through the how. So we'll go through actual examples. We will start with a question answering bot that works with structured data, so it can connect to relational databases, answer questions from there. The second practical example will be a question answering bot that works with unstructured data. So this can be your PDFs, your websites, or even semi-structured data, your JSONs, whatever. And to top it all off, we will combine everything we learned into an agent, a chatbot that you can converse with, and that agent can also trigger some actions, some tools if you tell it to. Okay, so like I said, this is a more beginner-friendly workshop. It's targeted to those who want to maybe dip their toes into the world of large language models applications. So it might be too introductory for some of you. It might be too advanced for others, although hopefully not. But I hope that we all learned something today. And also, if you have any questions at any point during the workshop, feel free to interrupt us. We can answer it right away if it's relevant, or then we also have some Q&A time at the end. You can also ask questions in the chat, and we will, whoever is not talking will stop the other one and ask the question. Okay, so without further ado, we can begin. Oh, okay. So with further ado, if you want to follow along, we've prepared a GitHub repository that contains all the code and the presentation. So if you want to follow along in the Python notebooks, feel free to do so. Luka, will you paste this?
I will write it into the chat because I didn't have it ready.
So Luka doesn't have it ready, so he will write these URLs for you, so you can just click and not type it yourselves. But yeah, this GitHub repository contains the code, the Python notebooks that you can use to follow along. The only thing that you will need though is an OpenAI API key, because we are using the ChatGPT API for our demo. Luka, how is it going?
Yeah, I pasted it, but it's not a link for some reason. I don't know. It's fine.
It's fine.
We'll figure it out.
Okay. You'll figure it out. Okay, so now without further ado, we can actually begin. LangChain. What is LangChain and why do we actually need it? So LangChain is a open source framework for developing large language models applications. These are applications that have large language models at the heart of them, and they then build around that with some additional components. LangChain as a framework provides some useful abstractions. It provides us with pre-developed interfaces, pre-developed components that we can quickly use to develop or prototype large language models applications. At the same time, through the last year, LangChain has grown into a fully fledged ecosystem. So now it's quite a rich ecosystem, and it allows for productionalization of applications developed in LangChain. So is LangChain the only framework that does this? Of course not. There are other open source alternatives, such as Llama Index or Haystack, among others, of course. And all of the things that we will discuss today are actually applicable with all of them, because they all try to solve similar developer problems and have quite similar abstractions. Okay, so why is there a necessity for such frameworks like LangChain and others? Large language models, either available to us through an API, or even if we're self-hosting an open source alternative, they're stateless. They don't have any context, they're not aware of external context, and they also don't have memory, so they don't have any conversational ability. In this visualization, we can see how a typical call to a, let's say, OpenAI API that we commonly use would look like. So we have some question, we can send it to the LLM and get some answer back. And this is perfectly fine. Using LLMs in isolation like this works reasonably well for simple applications. But building more complex large language models application will usually require additional components. And this is exactly where LangChain and other frameworks come in. Their main added value is that they contain these composable components that you can use, and these things pretty much streamline the development process of developing large language model applications. Besides this, they also offer many pre-built architectures that we can use almost off the shelf, and this truly simplifies the development of LLM applications. So examples of such components are, for example, a prompt template from LangChain. A prompt is some instruction that we can give the large language models to tell it how to behave and to prompt it to answer a question or do whatever. Now, of course, you can have this prompt and send it directly to the large language models, but LangChain provides these useful abstractions, and this can help, for example, with managing prompts. You can plug in play, you can change prompts, you can do whatever about it to streamline the development process. So in this example, we can see that, okay, our whole talk is MBA centered. Not that we're particular fans, but we just need a topic to center the talk about, and sports and positive vibes was the idea here. So in this example, yeah, we have a question. We can give it to some prompt, and the model can then answer the question. LangChain, of course, provides other useful components. For example, we can connect our LLMs to a vector store. A vector store is just a database that could contain some relevant documents, and we can then put this into the pipeline and add these relevant documents to the context, and the LLMs can then see this data when generating the answer. So in this example, these relevant documents might contain some information about the age of Nikola Jokic. So, yeah. Okay. Yeah. So one of the main selling points of these frameworks is that they are modular in nature. They are designed to be modular. And they also integrate a lot of other tools. So this means that we can change different LLMs. We can change the provider of our vector stores, and we can do that without many changes to our code base, which is nice. Okay, so through the last couple of slides, we have visualized the core concept of LangChain. As the name suggests, this is the concept of chains. So chains, basically what they achieve is that we can tie different components of LangChain together into a single pipeline, and then we can run this pipeline end to end from the user input to the LLM response. Chains can be arbitrarily long in LangChain. We could, for example, here add additional components if we decide to do so, and they can also be dynamic. LangChain, for example, provides an agent framework, and an agent is just a chain that can decide on the next step itself. So basically, at any given step, it can decide if or what it wants to do, if it wants to do something. Okay, so this was a basic introduction to LangChain. And I think that at this point, it might be best that if we take a look at how all of this is put together through a practical example. So I will let Luka take over, and he will showcase question answering bot over structured data.
Hi. Oh, how do we do this? Oh, yeah, great. Hi, my name is Luka, and let's see our question answering bot over structured data. So for the data set, if we start there, we'll be looking at, we just took a data set from Kaggle, basically no pre-processing. We removed some missing data so that to not confuse the agent, but other than that, we have games from 2004 onward. They will be split into five tables. So we have some general game data, game details, information about players, ranking of teams on standings of teams on different dates, and some general team data. If we take a look, just information where they're from, where they play, what is their home court, the capacity, the latest general manager, owner, head coach, and everything. So this is the data we're using. I think that this is pulled straight from the NBA API. Yeah. Okay. So it should, let's say we trust it, and let's see what we can do with it. So the first thing, okay, I said that there was minimal pre-processing, only some cleaning. In reality, there was also a lot of name changing because we decided to go with this workshop really LangChain centric. So we didn't do a lot of custom code. So in order for the model to better understand what's going on, we try to be as descriptive as possible with the names of the tables and the names of the fields by themselves. So everything was changed to be to try to be as clear as possible to the model, so it will work. It will work demo ready, let's say. If we take a look, so most of the things we will need in this example is just LangChain. They really abstracted everything, and when I say everything, I mean everything, as you will see. So the dependencies here look like it's only LangChain, but they import a ton of stuff. So if we get ready, what does our LLM need in order to understand our data? So what do we need to pass to the LLM so that it will know what it's operating about? If we, so of course, we will have to first explain it to him who he even is. If you worked with LLMs before, you know this is usually done through the system prompt. So the system prompt is something where you describe to the LLM who he is, what he does, how he has to act, and so on. As an example of a system prompt, it's right here. This will be the prompt we'll be using for this example. This prompt is taken directly from LangChain. I don't think, no, this is an unchanged prompt. And if we take a look at it, you explain to the agent, okay, you're a PostgreSQL expert. So right at this point, we already define to him what's the flavor of SQL that we'll be working on. This is very important later on because we want him to create the correct PostgreSQL queries and not, let's say, MS SQL queries, because there are minor differences and you can have problems if the agent is not aware of that. So that's one of the things. And the other thing that we will have to somehow explain to the LLM is the structure of our database. So how the database even looks like, because if we're just telling, hey, here you have a database, generate a query for it. If he doesn't know which tables are available and which columns in those tables are available, obviously it will actually it will generate an SQL, but it will be very generic. So it would just like select name from game data, where name where name equals Nikola Jokic or something. So we will pass to him this table info into his into the system prompt, where so he will be aware of the structure of the data and be able to write proper and correct SQL queries. And in the end, obviously, we also have to input the question itself. If you're with me, you might see, okay, but there's another thing that you need to put into this prompt. Yes, this is this top K parameter. So with language and data from a database, you might realize that it could be problematic to dump an entire table in text format into the LLM. Okay, the first problem is, as I'm pretty sure many of you know, the amount of data we can fit into an LLM is finite, so it's not infinite. We can't just dump everything in. Even if we could, probably wouldn't be optimal because of the limited reasoning, limited capability it has to understand everything when you dump a lot of data inside. So it's better to be very specific and very exact with what the LLM sees through text. So for this, we limit within both the system prompt and the actual code behind it, how many results we are actually at most returning to the LLM. So, and of course, this has to be explained to the LLM, so it doesn't think that if it gets, let's say, a standard value here would be 10, if it gets 10 results, that's all the data there is. But it's like, hey, these are the top 10 results, but there's more. Okay, we can run this, nothing special. So we just define the prompt, and then LangChain uses these prompt templates where you define the input variables. So we have input, table info, and top K that we will need to fill into our agent, and then the prompt itself. Great. Now the obvious next step is that we need the LLM itself. So this will be done by just today we'll be using OpenAI's API, and this is nicely abstracted to us through Chat OpenAI class. So we just imported it and then set temperature and choose the model. Another thing we will need is the connection to the database. Again, this is abstracted in LangChain. So we just connect to the database through the URL of the database, and everything is handled from there on forward. We can look. We can look like what this looks like. It's basically just an abstraction of, I believe, what are the queries based on? It's probably nothing here. I think it's I think it's the SQL Alchemy behind. I think they're running it just SQL Alchemy, and then what they do is just abstract classes and handle events, so that when you call an SQL, that everything in the background is okay. So this is an SQL, it's run, and then it's returned in a way that it's friendly to the LLM. So one of the main things that needs to be handled is the errors. You don't want the program to crash when an LLM creates a false SQL query. So that's usually caught and then passed back to the LLM as an error in text, so that LLM can fix itself. Today we'll be using the LLM can fix itself. Today we'll be using the GPT 3.5 Turbo 16K because it's cheaper than GPT-4 Turbo, and we might use the GPT-4 Turbo later on in the agent example. But for this one is strong enough for the examples we'll have, and it's just basically what we'll be doing. You'll see it just sticks to SQL, run the SQL, return and answer the file. And if we take a look how this looks like, in this example and in QA unstructured, we'll be using something that LangChain calls LangChain expression language. This is their way to kind of create chains, agent, whatever object that is serializable in LangChain, and it just defines an object that is created of smaller components that are then executed in a series. If we take a look what we need, so we already had the database and the LLM. We'll also need to somehow handle the inputs that we defined for our prompt. So we'll have the input itself, which will be the question, followed by this string SQL query. Why do we do this? If we take a look at our prompt, how it's structured, you have we specify the format that we want the agent to work in. This is very important when you're working with agents, because in the end they will produce text. And if you don't know what the form of that text is, it will be very hard to work with it, because in order to do anything with the output of the agent, you will need to parse it and then form it into a way that fits your application. So the format here is we pose a question, put the question here, and then directly append the SQL query text, and we expect the model to only output the SQL query. We take the output of the model, run it, and then present the model all of this with the result and paste the result here, and then prepare the answer for him, and then expect him to reply with the final answer. So this is the entire workflow that we will do right now. So the first step is creating the SQL query. Then we will let LangChain handle running the query, getting the result, and then the LLM will answer based on the result and based on the result it gets. So if we take a look how a chain in this example will look like, we have so this runnable parallel input, runnable parallel. This is just a way in LangChain so that the chain can handle multiple inputs, and that you define that this will be runnable. It's a quirk of the expression language, so we won't go much into it. But if we look then, this is then chained together with the prompt that we defined up here. The prompt goes into the LLM. The LLM has a defined bind, and we bind to the LLM a stop word. So when you get to SQL result, stop, because we need to analyze the query and input the result for you. And we also note, okay, so what we will get from the LLM at this stage is so the SQL query and SQL result. And then we will know that we have to parse this away and only keep this part. If we take so following by this is this no operation output parser. This is just a standard basic parser that doesn't do much. I think it just takes the text and returns it, and then we strip it. So this is done so that you don't have any trailing spaces on either side of the SQL, so that there are no problems. There are no problems with running the SQL. Introduces the possibilities of the SQL to be wrong. And if we take a look at how this works now, we can have a question: what game did Luka Vranjes have the highest three-pointers percentage? And if we run this through our, so we only made the first stage now. So what we expect to get is only the SQL statement, right? So we bound the LLM to SQL result. When it gets there, it has to stop. And then we just return the string that it generated and strip it so it doesn't have any spaces on each side. And what we get at this stage is the SQL statement. So we what it wants to return, from which tables we see here. Okay, it made a join. Then where player name Luka Doncic and order by three-pointers percentage, this descending limit 1. Okay, so it will only, so the SQL query, if all of these names are correct, is probably also correct. It wants to return the game with where the three-pointers percentage was the highest. One good things about the chains is that you can also stream the output. By default, this I think is not implemented, but I mean it's implemented, but it just invokes in the background. But if you want to have if you want the experience to be more like if you use ChatGPT or something, it feels shorter if you stream the output back to the user, so he can see the tokens being built together instead of just waiting, and then boom, displaying the entire result. And okay, so we also we did this so the print is a bit nicer, so we can see the SQL statement with all the new lines that were not printed here. Okay, so this is how you would define the first part of our SQL chain using the LangChain expression language. Well, in reality, for a lot of basic tasks like this, LangChain has handled all. We already have chains defined that handle all the basic use cases. So obviously, we can just import the SQL database chain from initialize it with our LLM and database, and we will have implemented already the entire chain. So creating the SQL statement, running the query, returning the result, and then answering. We can take a look how this looks like, but I think it's a bit too much for now. But the main idea is the same. So you have the LLM inputs that are passed to the LLM chain predict. You get the result. If you can define, okay, if you want to only return the SQL, but if you want to only return the SQL, but this can then go into the run manager. You can the database here runs the SQL that we created, and then going forward, this result is appended here. This result will then be appended, and the LLM will be called again to form an answer based on the result from the database. And if we take a look how this looks like, so again, as we said before, we have this structure that will be defined in the prompt. So made out of an SQL query that goes into an SQL result, and then the LLM forms an answer. So everything that's in green was generated. Everything that's in yellow, we put in. Our tool will familiarize ourselves with tools a bit later on. But everything that's in yellow, we during the execution of during this execution is something that we added in based on the results from the LLM. So now we get the answer. Luka Vranjes had the highest 3-pointer percentage in the game with game ID with some game ID. And okay, we can now ask what game has an ID of this, and it will be super annoying and tell us this was a game played between teams with ID home team and visitor team. But again, this, okay, we want to know, okay, who were these two teams? And we see, okay, these were the Dallas Mavericks and the Charlotte Hornets. Okay, so in this game, he had highest 3-pointer percentage. But but this is kind of annoying. I think we can all agree, right? Yes, we need to have the IDs in the database because it's the way the whole structure is connected. But when we're talking to an agent, we don't really want it to communicate with us through these IDs, because this is like machine language and we want it to be human language. How do we handle this? As most things in LLMs, it's through prompting, of course. So we fix the default PostgreSQL prompt from LangChain by adding these two lines. So what we'll say is, do not return IDs of teams and players, instead return their names. When talking about a game, always mention between which teams the game was played, never just respond with its ID. It's like a quick and dirty fix for this one example. Of course, if this was if you wanted this to work more generally, there's probably a bit more that you need to do to get this working just the way you like it, so that it handles all the cases that you want to that you wanted to. But if we take a look now, what game did Luka Vranjes have the highest 3-pointer percentage in? Okay, Luka Vranjes had the highest 3-pointer percentage in the game between Hornets and Mavericks with a percentage of 0.667, so 66% 3-pointer percentage. Great, it's better, right? But as I wanted to show here, it's this looks great, but the problem is, okay, so what I'm doing here, I'm asking exactly the same question. And of course it will work now, but it didn't work yesterday. But one thing that, yeah, you know, one thing that we're not handling right now is the example, what if this SQL query is not correct, right? So because right now the model, the LLM and the prompt contain no direction what to do if the return from the database is like negative, if it's an error or something. One way to negate this is to use this. So the SQL database chain, if you've been, if you maybe caught that before when we were looking at the structure of its run, has this use query checker that you can set to true. What this does is that the query that is created is then passed again through the same LLM with a different prompt. Just says, hey, this is PostgreSQL. Are you sure that this query is valid in terms of like in terms of PostgreSQL, that this is a valid PostgreSQL query? But again, when it's not checking if it's exactly, it's not checking if it's what the question wants, just checking the validity of the query. But as you might imagine, if we're using the same model here as we're using there, this might not always be perfect, and it could fail. And there's nothing we do right now if there's nothing that we do in that situation. So that brings me nicely to possible improvements and things that are missing from this current implementation to make it more user-friendly and something that is actually usable. So if we first take a look at what is missing, so we don't have currently any ability to actually hold a conversation, right? So we ran this, and if we take a look, if we now ask a follow-up question, the current chain implements no memory. So perfectly, it also fails. So to show that it can fail. We currently have no memory. So what happened here? What was the response? And then we use a follow-up question. There's no. So the chain is stateless. It has no recollection of the past events, and there's no possible way to know for it to know what the game was. So we were talking about this specific game, and as you can see, also it made an error in the SQL and the double chain run, and the database return an error. The second thing is one we already talked about, so the ability to recover from its own mistakes. And the third thing that I think is quite crucial when you're asking general questions over data is the support for multiple queries. Because if you take a look at the prompt, right, the only thing that it can do is create a single SQL query, get the result, and then it's forced to answer immediately. What if it needed to like make 2 queries or maybe 3 queries, like get a result from one query and then feed it into another, or make a decision, hey, is this something that I want to further elaborate on, or is this good enough for me? So there's no support for this here. Obviously, okay, some of you might say, why don't we just do this? And yes, I hear you, but then for a simple question like here, what's the LLM supposed to do here? And then again, okay, so what if we need 3, or we can just copy paste again? Not really. It will be more expensive because you're running like 2 additional you're going to the LLM 2 more times than you need to, and you might get some funky results because the LLM is, hey, I have the result, why are you forcing me to write another query? We will solve this most of these problems later. What we won't solve is the possible improvements to our flow, to the existing flow, so what we have already implemented. So the first possible improvement is to have we have descriptive names of tables and columns in our database. What we don't have is additional descriptions, which really help. For example, what I mean with additional descriptions, there might be columns in the database where it makes sense to never perform exact matches on, like player name Luka Doncic. What if I only wanted to know who the best Luka is? Right now, what the model I presume would do is just try to match Luka. We can check. I hope I'm correct. I think I am. Yeah. Okay. What did it look? What did it return?
That's hallucinated.
Yeah. Okay. So yeah, that's hallucinated exactly. So we had no result, and then the model just said, "Hey, I'm gonna answer from like it's based on, I guess it's training data, but okay, we know this is wrong, right? We returned the result previously from the database, and it was 66.7%, not 45.7. So this is another case that we don't handle currently in our system prompts, the hallucinations. Nothing says that, hey, if you don't get any results, don't reply. So the model just said, okay, I'm just gonna, there's nothing in the data set. I'm just gonna tell the user what I know. So this is also something that we don't handle currently. And this, why did this return nothing? Is because we did the player name equals Luka, and of course all the players have the full player name, so Luka Doncic. And what you could do for the player name is say, hey, don't use the exact match, use like, and then it will try to it won't perform an exact match, and we will get all Lukas here. And that's something that you can define with better descriptions. Another thing we could do is add some few shot examples to the prompt. They can either be static. Hey, I want, if a question is like this, generate a query that looks like this. And if they can be static, we can just do, hey, here are 3-4 examples, or they can be dynamic. We have like a database of valid queries, and then match them to your to the input question. Andrej will kind of show you how that could be done in his QA unstructured notebook. So in that case, you would have there would be a question put in. You would add like a few short examples, probably here or somewhere, that were dynamically generated and were closest to the actual example that the model has to write. So if you have like some complex joins or something, that you already have that in there, so the model can just copy paste them. And for example, like complex joins that are often used, so that the model can just copy paste them and doesn't have to write it from scratch each time. That's all from me when it comes to the structured data. Andrej, are there any questions? You can post questions now if you have.
Currently, no.
If there are no questions, we'll move forward to Andrej, and he will show us what to do if the data is not nicely set up for us in a database where you don't have to do anything but just be hey model, figure it out.
Okay, it's me again. I'll just quickly move back to the presentation. And I want to introduce you to the concept of retrieval augmented generation. Retrieval augmented generation simply means that we are adding additional data from an external database and making it available to the large language model by adding it to its context so that it can use this external data when generating a response or an answer to for the user. Okay, so why do we need this, and why is this even good? There are several factors of why retrieval augmented generation is now quite popular in the LLM application community. One of them is the problem that LLMs are static. This means that once they're trained on these large corpuses, they have this cutoff point of where that training data is cut off. So, for example, if you used ChatGPT in the past month, you might have seen that if you try to ask it about some new recent events, it will say that it cannot answer because its cutoff point was, I think, November 2021 or something like that. So basically, you cannot talk to it about the last 2 years. They've since that retrained the models, added more recent data, but the problem remains. Another thing is that large language models are trained on publicly available data, so they cannot work out of the box with your private data. We can imagine a scenario. Let's say that we are a company who has lots of internal documents, and we want to build a chatbot that the users can use to ask questions about our internal documents. An example use case would be that we have newcomers coming to work, and we want to have a chatbot that can help with their onboarding process. Of course, LLMs don't have any access to this data. They cannot answer questions about it because they haven't seen it before. So oftentimes this can lead to hallucination. Like Luka showed in the example, hallucination is simply the problem where large language models generate factually incorrect data. It can sound plausible, often it does, but nevertheless, it is factually not correct. Another point is that LLMs are expensive to train. We want to use them as foundation models, meaning that we train them once, and then we can use them for many downstream applications. So it is then much cheaper to simply implement let's say a vector database and connect our large language models to the database so it can see the additional data without having to further train or fine-tune the large language models. There exist techniques for efficient fine-tuning, for example, LoRa, but even so, we need to understand that whenever we are fine-tuning on some data, at inference time, the data will need to be retrieved from the parametric memory, meaning that it's saved in the actual parameters, the weights of the model, and this will be noisy retrieval. As opposed to if we implement a retrieval augmented pipeline, the model will be presented with factual documents that are available to it, and they're not they're hopefully not noisy, but contain factual information. So an overview of how we do design such a pipeline is in this visualization. It would consist of 2 steps. First step would be the indexing process. This is the process of making the vector database that contains the documents. In this process, we would start by collecting all the relevant documents that we want to expose to the model. For example, I mentioned that we might have some internal documents in our company. This could be in form of PDFs. Additionally, we would maybe want to scrape some websites. We might have some database with maybe semi-structured data. And all of this we can collect as a document collection and expose it to the model. The next step would be the process of splitting these raw input documents into shorter documents. We will talk about why that is important later. But when we are finished with pre-processing the documents, we need to embed them. This is represented by this arrow. Embedding a document simply means that we calculate a vector called embedding, and this embedding holds some notion of semantics, of meaning of this document. And we will then be able to find similar documents based on these embeddings, because we want the embeddings of similar documents to be similar. And this is basically the idea behind the similarity search of a vector store. So when we store our documents, we are finished with the indexing process. And in the inference process, we can then use these vector stores as a retriever. And when a user asks a question, we can take this as a query for the vector store, find similar or relevant documents, put this in the prompt of the LLM together with the question, and then the LLM can take information from these relevant documents to answer the user question and produce the response. Okay, so let us move back to Python and see an example of how this is built in LangChain. The goal of this notebook is to build an MBA assistant which will be able to answer questions regarding the general topic of MBA. It can be about MBA, MBA rules, MBA players, stuff like this. Okay, so let's first import everything that we need, load the system variables that contain the OpenAI API key, and then we can begin with the first step, that is the document loading. So in our example, we will be using two data sources. One will be the official MBA rulebook, which will allow the model to answer questions about general MBA rules. And additionally, we will collect a small subset of Wikipedia articles regarding the MBA, maybe MBA players, and the model will be able to provide answers about that topics as well. So if we take a look at how this rulebook looks, this is an example of a rule. It's available in HTML. We will simply scrape all of these rules. This is the text that we want. We will scrape this text, put it in form of documents, and then at inference time, LLM will be able to retrieve, our pipeline will be able to retrieve this text, and the LLM will be able to generate answer based on the information provided in this text. Okay, so these are our URLs. So to load the data, for this step, LangChain provides us with the interface of document loaders. Document loaders are just objects that are specific for a source, and they can then load information from that source and return it back in a form of documents. LangChain provides implementations for different document loaders depending on the input source type. For example, we will mention PDFs. There are PDF loaders. There are HTML loaders that we will use. There are also other loaders, for example, Markdown for semi-structured data like JSON. There are a lot of possibilities here. So we will be using a web-based loader that takes in a list of web paths, which it scrapes, and it returns back the documents. So this will take a second. Okay, great. If we take a look at this document, we can see that it contains the text under page content. So this is the text that we will be querying, and this is the text that the LLM will see in its context. Additionally, if I scroll all the way to the right, each document is equipped with a metadata, which contains some additional attributes. Web-based loader automatically gives us the source URL, under the metadata, but we could have additional attributes here. For example, let's say that we want to classify each document in our database to a specific topic. So we would have a topic attribute here, and we will maybe have a topic for MBA rules, and all of these documents would fall under that topic. So this metadata can prove important down the line. For example, when we are implementing the retrieval pipeline, we can use the metadata to filter the documents based on it. So let's say that for some weird example, we would only want the model to see MBA rules. So we could filter the metadata based on this topic. And then our retriever would only be able to return MBA rules related documents. LangChain also provides a way for the model to write the filters for the metadata by itself. It's called the self-query retriever. In this retriever, the model actually infers the metadata from the user question, and it can then filter and improve performance in doing so. Okay, I mentioned that additionally we will use some Wikipedia articles. We will use Wikipedia loader with a query of MBA, and this will load a couple of documents relating to MBA from the Wikipedia. Okay, this should be done quite quickly. Okay, so we can see that we have information about the MBA, some player names, general MBA topic. Additionally, because this is a Balkan-specific audience, we want to have we are hard coding in some more relevant topics for us, and just adding them to our collection of documents. Okay, so in total, we have 26 documents in our collection. This is a rather small collection, but it will serve the purpose of this demo quite nicely. The next step that I mentioned in the indexing pipeline is the process of splitting. So in this step, we would split original, potentially long documents into smaller text segments. So if you take a concrete example, this MBA rule at index 11, which is totally not cherry-picked, is quite long. It contains 32,000 characters, and it contains 6,700 plus tokens. So this can be a problem in more for several reasons. So one of these reasons is purely pragmatic. LLMs work with a limited context length, and maybe 6,700 tokens might not even fit in the context length of a large language model, meaning that it can't even see the whole document. Now, this might not be a problem for these newer models like GPT-4 that has a 32,000 context length limit, or even 128,000 context length limit. But if we're using older models or even open source models, they might have a context length limit of 4,000 tokens. So this is not acceptable. The other reason is that splitting the documents helps to optimize the relevance of the content that we get back from the retriever. So imagine this scenario. Let's say that we're using this very long document. Now, obviously, this document contains lots of information, and this information can be quite diverse. So in the process of representing this document as a vector, as a single vector, this vector will need to have some notion of the meaning of the entire document. And if we have a set of diverse information in this document, then this vector might not be optimal, and the results that we will get from our retriever will be suboptimal. And this is not something that we want. Furthermore, even if we get the correct document back from our retriever, it can happen that the model, because it sees this whole mess of a document, might not produce the best response, because this document contains the relevant information, and then it can also contain a lot of noise because it's so long. So to summarize, the main reason for splitting is to ensure that what we are embedding are pieces of text that don't contain much noise, but they are still long enough to be semantically relevant to a possible question. In our scenario, we are using the recursive character test splitter, which is a rather basic splitter implemented in LangChain, but it works quite well for this case, and it might prove quite useful also for lots of use cases. So the way this works is that we can specify the chunk size and the chunk overlap, and this will recursively split a document given this chunk size, where the chunks will be overlapped by the specified amount. So this overlap is quite important to make sure that each chunk contains all the semantic information that we need. So imagine a scenario in which we are naively just splitting the document, and we have, let's say, a piece of text that should be together in a chunk because it's semantically relevant to itself, but we naively split it in two. So now each of these chunks is useless to the model because it doesn't contain all the relevant information that it could use. So in order to mitigate this, we implement an overlap. And now when the chunks are overlapped, we like to pretend that each chunk has all the information that a model could use. Okay, so if we run this, this goes through quite quickly, and then we can see that we have split the original 26 documents into 346 documents that are now much shorter, but more manageable in terms of an LLM. Okay, so now that we, let's say, concluded with the pre-processing step, so we collected the data, we split the data, let's say that this, excuse me, this is all the necessary pre-processing. We need to embed and store the documents. So in our case, we'll be using this simple vector database called FICE, but in your solutions, you might want to use an managed solution such as Pinecone. You can use other open source alternatives such as Weaviate, but here we just set up a FICE vector store because this is probably the most simple thing that we can do. So in this step, which is just one line of code because everything else is abstracted by LangChain, the following thing happens in the background. So for each of our 346 documents, we will compute a vector representation. In order to do that, we will use OpenAI ADA model, which is the reason why we use this in this example is because it is the most streamlined solution because it is managed and we can just call the API. So this call to this will result in 346 embeddings that we will store in our vector store, and then the retriever will be able to also use this service to embed the query and then compare all the vectors of the query vector to all the available vectors, and the most similar vectors will be deemed the most relevant. So this, we can run this, and this leads us to a vector store. Do I need to run this?
No.
Okay, you already have this.
You can explain.
Okay, yeah, we can just, this line, all this line does is just saves the vector store to a file on disk, because this is, if we don't do that, this is just in memory and it's not persisted. whereas this is something that we can do to save it to disk, and this is something that we will use later in the agent framework. Okay, so now we've concluded with the indexing part of the pipeline. And the result is a vector store that contains all our documents. And now we can move on to the actual LLM application logic. The first thing that we will need is a retriever. Retriever is just an object that can query the vector store given a user question and return the most relevant documents. So we can specify it directly as this from the vector store, and we can input it with some arguments. For example, here we said that k equals to 4, which means that the retriever will return 4 documents from the vector store. So let's say that we have a question: how old is Nikola Jokic? And we can see that we get back some documents that talk about Jokic. I'm not going to read them and check if the information about his age is actually present, but okay, well, it is present. So this works. So here we have specified a fixed amount of documents. In some use case, we might want this to be dynamic, so that maybe we have a cutoff point based on the similarity score. But for our use case, having a fixed size or fixed length of the return documents is good enough. Okay, so now we have implemented the retriever, and we can put everything together to a retrieval augmented generation chain. So this is just a helper function that will join a list of documents together in order to give them to a prompt. Luka already explained prompt templates in LangChain. The one we are using here is we are just telling the LLM that it is a helpful assistant that can answer MBA related questions, and we tell it that it will receive a context. The context will contain relevant information, and it can answer the question based on this context. We have then 2 variables in our prompt. So the context variable is something that we will fill with the relevant documents, and then in the question variable we will put the user question, and then the model will then generate the answer. We are in this example also using the GPT 3.5 Turbo, and we're setting the temperature to 0 because we don't want any stochasticity here. We are fine with being more or less deterministic. Okay, so this is how we can define the chain, and this illustrates all the parts of the retrieval chain. If you take a look at this pipeline, so we have a vector store. We given the question, we can retrieve the relevant documents. We give all of these variables to the prompt. The prompt is used to prompt the LLM, and the LLM gives us back a response. So this is exactly what we implement here. So the question is just the question that we input, and the context is first the question is given to the retriever. The retriever will return a number of relevant documents, and we will then pass these documents to the function format docs, which will simply return a string concatenating all the documents. This is then passed to the template. The template will use these variables to construct the final template, the final prompt. This final prompt is then sent to the LLM. LLM will produce the answer, and then we just want the text of the answer. So we use the string output parser. So this is basically how we can chain different components of LangChain to produce a retrieval augmented chain. Okay, so let's test this thing. Let's say that we have the same question as we had before. So how old is Nikola Jokic? So this is the information probably that the model sees, given that this is what we've seen here. And presumably this math is correct, and Nikola is actually 28 years old. We can test different questions. So for example, we can have NBA rules question about how many referees are in a game. We can have maybe some more generic history questions about the NBA. So LA Lakers and Boston Celtics will both have 17 championships. And this is basically it. We built a retrieval augmented chain for each of these questions and answers. The retriever first finds all the relevant information. It gives it to the model, and the model generates the answer. Now you might be wondering, couldn't the model generate the answers itself? It probably could, because these are all maybe general knowledge things that the model has seen during training. But this example illustrates that maybe in an example where where the model doesn't have the data, it can still output the answer based on the relevant documents that we give it. In our prompt, we have specified that the model is a helpful assistant for MBA-related questions, and if it doesn't know the answer, it says that it doesn't know, it doesn't try to make up an answer like it did in the SQL example where it hallucinates. So for example, if we ask some random question, like what is the meaning of life, the model, because it doesn't have any relevant information in the context, because actually no one knows this, it answers that it can't answer the question. Okay, so this next example illustrates a point that Luka already made. And that is that our chains are currently stateless. They don't have any memory, and that means that every call is not dependent on previous calls. So this can be problematic if we want to have a conversational ability with the agent. So for example, if you want to ask how old is Nikola Jokic, the model says 28 years old, and then we want to know, and how tall is he? Because the model is not aware of this previous question, the model doesn't know what this he refers to. So presumably this will fail to answer correctly. Yeah, okay. So yeah, that is exactly what happens. So the first answer is about the age of the Joker, and the second answer is regarding the height of Luka Doncic, which is not what we want to know. So okay, we can actually check that the model can actually answer this question. So as you can see, the model can answer this question. It just didn't have the context to what this he refers to. So we decided that adding memory to this workshop, that adding memory is out of the scope of this workshop, but nevertheless I want to give you an example of how one might do it. So I have a visualization here of how one might add a retrieval augmented chain that also has memory. So in order to do that, we now have two input variables. We have the user question, like we did before, but now additionally, we have the input variable that contains the chat history. So this is all the previous messages and answers in the dialogue. So how one might construct a chain like this is that we first have an LLM call that that takes in the user question, and it takes in the chat history, and it combines this into a new standalone question. The idea here is that this standalone question contains all the relevant information for the model to give an answer. It's not just the new user question, but it's also information from the previous questions. So for example, in this case, we would want the first call to join these two questions, so that the standalone question would be something like this: how tall is Nikola Jokic? Because the model would replace this pronoun he with the full name, because this is the information that the LLM needs. Once we get the standalone question, we can simply follow the normal retrieval augmented generation pipeline. We put it to a vector store returns some relevant documents. We combine the question with the documents into a prompt, and then this is returned to the LLM, and the LLM gives a response. Okay, this is more or less it for this example. Luka, do you want to take over?
Yes.
Okay, so now we looked at two examples of retrieval augmented generation. One was consisting with structured data, in which the model was able to query an SQL or any other relational database. And this second example introduced that how the model can query unstructured data, for example, websites. This last example that Luka will talk about will tie everything together in a fully functioning chatbot, which will be based on the agent framework. But I will stop talking and let Luka do the showing.
Thank you, Andrej. I wanted to have a quick intermission before we go forward with agents. And I wanted to shout out, if you're interested if you want to know more about retrieval augmented generation, there is what I believe will be a fantastic talk at the DSC Europe, if you're there live on Wednesday in Congress Hall B at 12:15. Špela Luka and Vranjes will have a talk on the retrieval augmented generation. So I believe that they would love to see you there. You're all invited. And I'm sure, so this was a very technical part. So this was very technical, but I'm sure there will be a lot more, more theoretical example solutions and how to tackle problems connected to unstructured data and retrieval augmented generation in that talk. Anyway, let's move on to the final stage of our workshop today. We'll be creating a multipurpose agent. For this, we'll be using the agent framework that's available in LangChain. And if I just read you, so how they the idea behind agents, how they describe it in their docs, is the core idea of agents is to use a language model to choose a sequence of actions to take in chains. A sequence in chains, the sequences of actions is hard coded, as we've seen before. So when I was showing you the question answering over structured data, we saw that the model was only capable of performing a single SQL query, and then it had to generate an answer, right? In agents, we let the model be more free, so to say, so it can determine itself, more or less, which actions to take and in which order. The core parts of this agent framework are agents itself. So this denotes the chain that is responsible for deciding what steps to take. The tools, these are functions that an agent can invoke. We'll see later on how they're presented to the agent and how we define them. Toolkits, these are sets of tools. The main idea behind toolkits is so that you can predefine a set of tools that help you manipulate or work with a single application, or that are designed to work together to achieve some goal. And the last part, and I would say maybe the most important part of the entire framework is the agent executor. So this is the runtime of the agent itself. We need the agent executor to kind of tie everything together, because agent in this framework can only we said we can let it to determine which actions to take and what to do, but as we've seen before, we can only specify for we can only define single steps that the chain can take. What agent executor does is helps us manage that and connect them together to something that resembles more of a thinking agent. So an agent that can take multiple actions, can reason based on the outputs of those actions, and then respond to you based on its findings. And so agent executor is the main class that handles that. It also handles logging and all that additional tasks that are much needed when you actually need to see what's going on, troubleshoot, and make the entire structure work together. So if we start in this example, we will work only with like private components. The only thing that we will do kind of custom is the prompt for the main agent and the prompt for the main agent and the tools that our agent will use. So again, what we need, as we've seen before, we need the LLM itself, the connection to the database from the structured part that we've seen. Then we will actually not be using the SQL database toolkit. This is just something that I wanted to, because I simplified this example a little bit to make it easier to understand and easier to prepare the system prompt for it. We can take a look. So what this SQL database toolkit actually is just a collection of tools. In this example, we have 4 tools. A tool that lists the tables that are in the database, an info SQL database tool. So this is a tool that when provided a list of SQL tables, returns the descriptions of those tables to the model. Then we have a query SQL database tool. So this is effectively what we've seen in the before when I was presenting to you. So this is the tool that takes an SQL query and returns its output. And then we have also a query SQL checker tool. This is again, I've showed you before, you had that option that every query is checked. So here it's not a must. If something goes wrong, the model can decide, hey, query SQL checker tool, can you check for me? I thought that this query was correct, but the query tool is saying that it's not. What's up? And the query SQL checker tool can fix it for him. Ideally, it's not always the case. It depends how good of a text to SQL model it is. Oh, my bad. I also wanted to talk a bit to show you a bit more of the other toolkits. So if we take a look in the LangChain library, you have many toolkits, like a GitHub toolkit that basically implements all the functions that you would need to talk with GitHub. And as far as I know, this is directly then connected to the GitHub API. So basically, the functions that are available to the model are the GitHub API, whatever GitHub API supports. Maybe if we look one more, Gmail. So integration with Gmail. You can create drafts, send message, search through Gmail, get message, or get thread. So these are all pre-implemented together with like their descriptions. So if you wanted to work with Gmail, all you need to do, so you need to give it an API resource, and then the agent, you will have the pre-implemented functions to work with Gmail. Well, but as I said, we won't actually be using this today because we're making an MBA agent, and the main idea here was to show you, okay, how do I define my own tools, and how do I then give them to the agent so it can use it. Another thing that we will more or less gloss over, as Andrej alluded to, is this conversation buffer memory. So this is a memory that we will give to the agent. This is just a class that will remember our conversation, and then on each call feed this chat history to the agent, so it will have this context of what's going on. And the last thing that we will need, that we have already talked about, is this FICE vector store that we will use as a retrieval that we have already made, that Andrej made for us in the previous step. We wait for everything to initialize, and then we'll start looking at tools. There are 2 or 3 different ways to create initialized tools in LangChain. I prefer this way, so where every tool is its own class, an extension of the base tool. Why do I prefer it? I don't know. I just think that it looks better, and it's easier to have a good overview when you're searching something. It has a clear structure. It requires to have a name and a description, and then you just define a run function, which enables you to have a lot of control over what's going on in the tool. This is a standard query SQL database tool that I just copy-pasted from the SQL database toolkit. This is the only tool that we'll be using, and I'll show you what I did to kind of simplify this problem to not require the other tools. And this was possible because our data, we don't have that big of a database, so we don't have thousands of columns and tens, hundreds of tables that would kind of prohibit us to do this hack that you will see a bit later. Another thing that so we've seen the question answering over structured data, we've seen question answering over unstructured data. Another thing that we wanted to show you here is how through tools agents can interact with APIs. So what we've decided to build is like a very simple fast API for like a MBA scheduling ticketing system. It's very simple because it only has 2 endpoints, schedule and reserve a seat. And what we will do here is we implement tools to interact with with that API to enable 2 things. The first one is to check a schedule. What this tool does is it takes an input, so it takes a date in the format and outputs a list of games that are happening on the corresponding date. So a list of games together with their game IDs. The game IDs are internal, or
no? This is actually an MBA schedule.
Okay, so I didn't implement this. Andrej did. So we're taking from the actual MBA schedule the games that are being played together with their IDs. And then the second tool. So we see this is very simple. It just we do an HTTP request, very secure on the local host for a date, and just return the response. And we kind of wrap the response in some additional text. Wrapping the response in additional text kind of help us control what the agent does with the information provided by a specific tool. This is quite a useful thing that you can do to help you steer the agent in the correct way during execution, not only through the system prompt. The second function we have is the reserve seat function. Again, we just create a post request, for an ID that we got from the schedule, and then it can either be positive or negative. If you wanted to know how this works, it's a 50% chance that we get a reservation and 50% chance that we don't. Keeping let's hope we get that seat later on in the example. We'll see. I forgot to run these tools, and the last tool that we will create is what Andrej created for us in the previous example. So the retrieval augmented generation. Here we will not always input what we find as relevant data to the agent as we saw before on every call, but we will let the agent decide when it thinks it needs information from either the rulebook or Wikipedia, and it will allow him to call this tool with the query. So what he's interested about, as you've seen before, we will just run this query through our retriever, and then package the relevant documents here in a nice prompt that kind of helps us, again, as I've said before, kind of steer the output where we want to go with this information. And yeah, we'll see how this works. We put all the tools in a list, and the last step that we have to do before we test it out is defining the system message. Now, here for the agents, this is a kind of a Frankenstein system message that I put together from different system messages that were created for LangChain. It works for the questions that are set below, hopefully, but it's not very bulletproof. So creating a system message is prompt tuning. If you're creating a system that you want to be more strict, to behave predictably, but also answer the questions in a polite manner with only factual information, there's a lot more that goes into creating this system prompt, and all the prompts that we won't be looking into right now. I can show you a bit how everything is structured, but this is the only thing that we will be modifying. This is not even the whole system prompt. That is, I think it's I think this is the whole system prompt, but it's passed on in how this agent is put together. But there are many ways that a lot of these things can be done. So what we do, we obviously gave a name to our agent, call him Mr. MBA, and tell him the current date so that he can. This kind of helps him to know what day it is today, because he's a large language model. He kind of has no feel for time. The other thing that we tell him is that he will have to answer our questions, that he can work with a PostgreSQL database, that we don't allow him to make any insert, update, delete, drop statements, that he can only make select statements. And as before, we don't want him to returning IDs. What we want to see the names of the teams and players, because as we've seen before, if it returns your ID, okay, great, it works, but it's not really human readable. The last thing that I want to show, so this I kind of hacked this in here. This is the information about our tables and columns that we have in the database. We kind of simplified this here so that we don't need all the 4 tools that the SQL database toolkits implements, but we only need the query tool, because everything else is already available to the model in its system message. It does make the system message a bit bigger, but since we expect that the database will be often used when talking to the agent, we kind of take that hit. To put together the agent, we use this initialize agent function, what do we specify? So we specify the tools, the LLM, this agent type. We can take a look at what this is, and these are some pre-configured agent types that are available in LangChain. We want to see what's happening, so verbose is true. We give it memory. We give the agent the system message that we defined, and we put this handle parsing error. So true, this just makes the agent a bit more usable. So if the output of the generation is not something that our parser can handle, you will see when I run the agent what I mean. It kind of handles its own errors. It doesn't just let it go through. Before we go to the examples, we can kind of look at like the different agent classes that are implemented, that are pre-implemented in LangChain. If you're doing a more serious project, I would suggest it's probably better to go with a custom agent and using the LangChain expression language, or maybe taking one of these and probably heavily modifying it to get to a state where you'll be happy with the agent. So what are some of the agents that we have, like the zero-shot React description? So this is a simple agent that does one action. What we'll be using is this chat conversational React description. Basically, what these agents have implemented is how the prompt for the agent is structured. So we can see here we put the system message. After the system, at each call, we have the system message. We have the message, we have the chat history, we have the human message, and then an agent scratchpad. And I will explain what this agent scratchpad is a bit later. And so everything, how the whole things run is then defined in the agent, where you have all the functions that are called in the background. We probably don't have to go that deep. It's a bit beyond the scope of this presentation. So, okay, now we have an agent. Let's see how it works. Okay, so this is just a quick test. He knows he's Mr. MBA, which is very important. And now can just, because we've given him this memory, we can talk to him, and now he's aware of the previous questions, and we can, as you will see, we'll be able to like ask sub questions and more. I like this response. It was a game between Dallas Mavericks and another team. His 3-point percentage was 0.67. Okay. This was set up here because sometimes he didn't answer this, but I guess we can skip it and kind of ask him what was that other team. Okay, now we see that it has kind of this memory, knows that we're talking about the game where Luka Doncic had the highest 3-pointers percentage, and it returned the game that which can return us when and who played in that game. And now we know that that was a game against Charlotte Hornets while playing for the Dallas Mavericks. It decided to not tell us when that was, but so this is not a very rigorously defined in our system prompt. So the outputs can be a bit finicky. So another thing that I've shown that we've implemented is this tool to check the schedule. Oh, yeah. Well, it's probably smart to run the server API before I check the schedule. And now again, so we have that memory, we can just continue asking him the question, and the agent itself decides what it will do. So here, before we see, okay, it created the SQL double query, and now because we ask him about like further games, hey, let's check the schedule. I don't need to check the database in this example. It looks like something might be broken. Let's stop it and restart. We can just go on from here. The OpenAI API can sometimes be a bit finicky and kind of hang, not ideal, but well, you have to deal with it. Okay, so we see that we can ask him for about future games with a given date, and it will then check the schedule. It will call the API that we have created here. The API returns us this list, and we pass this list to the model to then kind of parse it and respond with what appropriately depending on what the question was. Because we were specifically asking about Dallas games, it only looked at the Mavericks games, and we can see that the Dallas Mavericks will be playing the Memphis Grizzlies on the 2nd of December, and it also outputs this game ID. This is kind of hacked in because we need a way to pass this game ID then to the reservation function. So I made him keep the game ID in the response to the user by basically defining in the tool response to the user with the appropriate matchups and the corresponding IDs. So so that we can have no IDs when we're asking or less IDs when we're asking for when we're using the SQL double query. But here we need to have this ID so that we can then reserve a seat. And we didn't get a seat. Well, Andrej put the percentage chance too low for us to reserve a seat. If it was like more 99%, then we would get a seat. Maybe if we ask it politely. Whoa, the seat cleared up. Yes. Great, we're going to the game. So yeah, and the last thing that I want to show you. So we're showing the SQL double query. We're showing you the check schedule and reserve seat. Another thing is the querying over unstructured data. In this case, the model correctly uses the rulebook and wiki info to retrieve three documents, and then responds to us with the response. So Nikola Jokic started playing in the NBA in the 2015-2016 season. Great. And now, so we can just continue, right? We have that memory implemented. We can ask what was his best game in terms of 3-point percentage, and it will correctly, it won't ask the rule book or the wiki, but we'll go to the database, find the correct game, and he had 100% 3-point percentage in this game. So beating Luka's best game, that was 66.7. 1-0 Serbia's lead, I guess. And we also see another function that we kind of now have with this agent structure. The first query that the agent created, the first SQL query was incorrect, so it returned an error. And how this is handled in the structure is that the error is, so we don't just crash the system, we put the error into a string and return it to the model so that it can analyze the error and fix the problem to then correct the SQL query and get the response that it wanted. So it doesn't just crash. The model, the agent itself is structured in a way where it can autocorrect in cases where there are mistakes. And again, so we have this memory. I don't know how this will work. Sometimes what happens, especially when you're using, I think this will be a great example. Yes, it will be. When you're using when you don't have any specific guardrails in place, the agent is allowed to make at most like 15 different calls. And if you're using temperature 0 because you want it to be very exact, sometimes the agent, with how it's structured by default, will just loop itself. So it's just doing the same thing over and over again. It's unable to autocorrect, and we'll get a response with agent iteration limit reached or something. It takes a bit of time and money because we just made 15 requests to the OpenAI API. But yeah, so this is an example of like still things are not as clear as could be. As like, well, I wanted to show you, okay, through these examples, so what works, what doesn't, how that it does work. It looks kind of impressive. It responds to questions. It has this knowledge about current previous questions. It can answer sub questions. It can use different tools. It knows how to use different tools. But still, to get this to like a production ready state, there's still a lot to be done. So yeah, another question. So how far away from the from where do I have to stand to get 3 points? So this is an example of using the rule book, because we used only the wiki before, and we see that it correctly points out that you need to be 7.24 meters away to get 3 points when you throw the basketball. This will be all from my end, and I believe Andrej has a question for me. I mean, not Andrej, but Martin Fresher. Okay. Hey, and he says, hey, I'm reserving a seat, although he reserved seat, the finalist was still based on failed reservation.
Read that out, because I don't know if they can see.
Huh? Yeah, okay. Hey, so Martin asks, hey, in reserving seat, although he reserved seat, the final answer was still based on failed reservation. This is probably because memory. I ask him this because I also saw that behavior in our project. Do you have any solutions for this, for memory to work better in agents? Yeah, so this is a great question. It's not a very straight up answer how to solve this.
Use a bigger model.
Yeah, so Andrej recommended to just use a bigger model like the GPT-4, the new GPT-4 Turbo, which is from our testing a bit better this. But yeah, so what we mostly do without like honestly saying too much is we handle we kind of have a way to handle good memory compared to bad memory. So we don't always keep everything in memory, and we don't always give the agent so yeah, the agent doesn't have ability to see everything, just what's relevant to the current input. And there are like different ways to achieve this. This is also done through better prompting. This is done through catching errors in the workflow in the planning stage. This is done through checking the results. You can do this through double checking. Of course, like double checking is kind of expensive in time. If you're working, if you're implementing an agent, you kind of want to have the response time as low as possible. So this does limit you in terms of what you can do. If you can afford a bit more like compute time, there's double. You can have like a separate chain or something, evaluate the response based on the current scratchpad and the history. Yeah, I hope I at least partially answered your question. I know it's not much, but maybe you can write us an email, tell us a bit more about your application. I'm sure that like it's hard to do here, but if you shoot us an email, we will take a look at it, and we can maybe give you a more appropriate solution, help you a bit more for your specific use case. It's very dependent, as I said. In our applications, we've saw that probably. Okay, can you give me one example? What? Yeah, sorry, I'm just going to the next question from Roman. Can you give me one example? What surprised you once you put the model in production? I think that with the models in production it's kind of hard to know.
You shouldn't be surprised when you put something in production.
Yeah, okay. So with the problem with LLMs is that like the space of possible solutions or even possible inputs that should theoretically lead to the same solution is like very large because we were using natural language. So looking at logs and looking at where then that your system failed, it's very hard to handle every use case. It's very hard to have like a broad set of testing that will handle everything. And you kind of, at this point, we kind of know that we can't create a system that's 100% good, right? There will always be edge cases. You kind of try to minimize that. Another thing that will obviously happen is that when you're developing a system, you kind of learn how to prompt it, and everything will look better than it is. So it's good to kind of get every like bigger update. It's good to have maybe someone from the outside, if you work like in a bigger company or something, come in and kind of test it to see, hey, how do our users actually understand what this is? How do they use it? Like, what kind of questions are they asking? Because when you're developing it, you have like a very strict mindset what you want it to be. And it usually turns out, hey, users kind of understand it differently. But that's actually just basic like software design problems. I would say that many of those problems are also applicable here. Also, I'm not super happy with the quality of OpenAI's API. It's kind of hit or miss. Like, it's not super reliable. You kind of have to handle those cases. Another question from an anonymous attendee: what is the main point of using chains? How is it different than just sending a prompt template? So I don't completely understand this question. You
probably why would you even use LangChain and chains if what you're sending at the end of the chain is a prompt anyway?
Okay, so why don't you just automatically handle this? Well, the direct question would be just it helps you use LangChain to help you develop faster.
Yeah.
There are plenty of things that are pre-implemented, and for when you need to show a proof of concept, when you need to quickly check if something is feasible, when you need to as I shown before, there are many like pre-implemented toolkits when you need to like test if something is possible, if that is something that you can add. LangChain just gives you the ability to like import the toolkits, add it to tools, and then okay, everything works or doesn't work from there on, and you can kind of gauge, okay, how much of added development would I need based on what I see to get this production ready. I hope I answered. If the chatbot gets another question from an anonymous attendee: if the chatbot topic gets complex and too deep, does it take too long time for processing each answer? Also, are the ChatGPT costs exploding when putting such system in production for many users? Yeah. So with the complex topics, the problem with complex topics and questions is also the design of the system. And yeah, then as you've correctly alluded to, the entire processing is can get long. All the steps that you need to do to keep everything in check, to keep everything factual, to even execute the correct workflow, because okay, all the examples I've shown you is call one tool and that's a response, or maybe like two at most. But with complex answers, you then have like these complex interactions between tools that you need to handle. It's usually best done with some more stricter control over the stages that the agent can take once executing something, and that can, I haven't seen. I think that can be very expensive, because also for complex questions, you also want to use better models, and having a system that is very like general, that can answer like these deep questions or very analytical questions. If you like putting it in production, I've seen it like on the back end, but not very user focused. So where the costs are more manageable, as you said, because if you're using like GPT-4 Turbo, the new one, the preview, and everything tuned for complex solutions, comes that like each query successive that can
speed up, Luka.
Yeah, we have 3 more minutes, so I won't be able to answer everything, but you can write us an email and we can chat.
Yeah, we have a slide about that.
Yeah, we have a slide about that. So I have 2 more minutes, or should I stop?
No, you have 2 more minutes.
Okay, which question is 2 more minutes?
They're both one answer question.
Okay.
One sentence answer.
Martin, thank you both. A very good presentation and good pace of code explanation. My final question would be if you can say a few words about any interesting use cases project you're working on, and can talk about that uses presented technology. Yeah. Okay. So
you can mention agent that connects to let's say a SaaS product.
Yeah. Not mentioning any specific company, but so we're working for a company that has like a system as a service, and what we're doing is we're creating an agent that interacts with the company's product, so that it can be integrated into different communications channels of companies that use their services, so that you don't necessarily need the UI anymore, but that their solution, their software is closer to the users and easier to use and to interact with. Then you don't need to learn like complex UI.
There are also many questions, I think.
Yeah, and like the generic question answering like over structured data or unstructured data, that's also very common. Last question: how do you choose the right chunk overlap size? Well,
trial and error.
That's trial and error, or if you're lucky, your data will have kind of natural breaking points where you can kind of use like some smart chunking, not just the default brute forcing.
Yeah, like based on titles and subtitles.
Yeah,
you might be able to split it.
Andrej said we also have one last slide. Where is it? Oh, here. Okay.
Question.
I hope I answered as much of the questions as possible. If you have any more, here are emails. Shoot us an email. We can chat. We would love to chat with you about this. We work almost exclusively on developing LLM applications right now. So we're also happy. We're always happy to chat with people that are doing the same in the same business, and to kind of share our knowledge.
Or if you have any LLM use cases, we are also willing to collaborate on some projects. So we are Luka and Andrej from Valera AI. Hopefully we were not too long, because it's also already 11 o'clock. Emilia, was it okay? We lost her.
She's not here in time.
Yeah.
I guess it's okay. Then.
It was fine. If
I'm here. Sorry, I'm here. It was very interesting. We are glad to have you as our tutors, and thank you everyone for joining us.
Do we need to give you back the control, or can you just take it?
No, I will take it.
Okay.
Thank you very much.
Have a nice day. Bye.
You too. Bye.
Thank you, everyone.